Today, we're going to look inside the digital fortress that's supposed to protect you online every single day. The question is it really as unbreakable as it seems? Let's find out.
Think about it for a second. Every single time you visit a website, you're basically inviting code written by total strangers to run on your machine. A security slip-up here isn't just a harmless error message. It could be your passwords getting stolen or worse. It's this constant tug-of-war between having a fast, interactive web and keeping you safe. And right at the heart of this battlefield is JavaScript. It's the language that powers basically everything you see and do on the modern web. But all of that power, well, it comes with a pretty big risk. And here's the catch, right? The very same complexity that makes JavaScript so incredibly powerful is also what puts a giant target on its back. Every new feature, every cool interaction is another potential door an attacker might try to pick. So to deal with this, browser engineers came up with a really clever solution. They built what you can think of as a digital padded cell for code, a fortress designed to contain anything dangerous before it can actually harm your computer. Now, the fancy technical term for this idea is software-based fault isolation, or SFI. The strategy is kind of counterintuitive. It's not about trying to block malicious code from running. Instead, it's about letting it run, but trapping it inside this confined space where it really can't do any damage. The most common version of this you'll find is the V8 heap sandbox. If you use Chrome or Edge or a dozen other browsers, this is what's protecting you right now. It protects literally billions of people by splitting the browser's memory into two distinct zones: a trusted area for all the super important security critical stuff, and then the untrusted sandbox. That's the padded cell where all the JavaScript code has to play. And this is the secret sauce. In the bad old days, code used something called raw pointers. You can think of these as master keys that could point anywhere in your computer's memory, which is incredibly dangerous. The sandbox gets rid of those. Instead, it uses offsets, which are like special keys that only work for doors inside the sandbox. So if a piece of code goes rogue, any damage it does is completely contained. So we have this fortress, this padded cell. It seems pretty secure, right? But what if the attacker isn't trying to break in from the outside? What if they're already on the inside? This idea right here, from the research we're digging into, just completely flips the script. This new threat model just assumes the attacker has already broken in. They have full control inside the sandbox. Their one and only goal now is to find a way to escape. And this creates a huge problem. You see, our traditional security tools, things called fuzzers, that just throw tons of random data at a program to see what breaks, they're all designed to test the front door. They're checking the locks from the outside. They're just not built to find an escape route from the inside. So, if you really want to test the strength of this sandbox, you have to invent a totally new kind of tool, one that can actually simulate this attacker inside scenario. So that's what researchers did. They built a tool called SbxBrk. You can think of it as a fuzzer that acts like a patient, incredibly clever attacker who already has total control of the sandbox and is now just methodically probing every single inch of the boundary, looking for one tiny weakness. So here's how it pulls this off. First, SbxBrk finds every single point where the trusted part of the engine has to read data from the sandbox. Then it intercepts that process, pausing everything right before the data is read. It then injects a fault. It corrupts the data, just like an attacker would. And then it just watches to see if it can trick the trusted code into making a mistake that could open the door. So what happened? After putting the world's most widely used sandbox through this absolute ultimate stress test, what did they actually find? Was this fortress really as impenetrable as everyone thought? Was that padded cell actually escape-proof? The researchers found 19 new security bugs, each one a potential escape hatch out of the V8 sandbox. And we're not talking about small, theoretical issues here. These findings were so significant they were officially verified by the ACM, a top computing organization. All 19 of these vulnerabilities, which could have led to anything from data theft to a full system compromise, were reported to Google and have since been fixed. So we're all a lot safer because of this work. And the bugs they found were pretty gnarly. They included some classics, like buffer overflows, where bad data tricks the trusted code into writing outside of its allowed memory space. They also found use after free bugs, which is kind of like tricking the system into using a key for a room that's already been demolished. but they also found some really subtle, insidious flaws.
Take the double fetch bug, for example. Imagine the trusted code reads a value from the sandbox and checks it to make sure it's safe, looks good. But then, a millisecond later, it reads it again to actually use it. SbxBrk figured out how to simulate an attacker changing that value in the tiny, tiny window of time between the check and the use, completely bypassing the security measure. Just brilliant.
And that really gets to the crucial point of all this. In this constant cat-and-mouse game of cybersecurity, even our strongest, most trusted defenses can have hidden flaws. It really proves that to secure our systems properly, our testing methods have to be just as clever and sophisticated as the attackers we're trying to stop.
And that leaves us with a final, maybe slightly unsettling thought. If the V8 sandbox, a system that protects billions of people, had these hidden escape routes, what other critical software that we all rely on every single day might have them too?